Hello everyone and welcome to our fourth webinar in Taming the Dragon series. My name is Daniela and I'm part of the marketing team here at ZettaScale, and I have the pleasure of introducing Carlos, our Senior Technologist, who will host today's webinar. He is going to talk about the challenges of software development for embedded systems, microcontrollers, and he'll also provide examples of the features that Zenoh uses to overcome them. He is also going to focus on Zenoh Pico, which is the lightweight implementation of Zenoh for microcontrollers. I can see that we already have quite a few people online, so I won't take any more of your time. So Carlos?
Yep. Thank you very much, Daniela, and hi everybody, and again, welcome to this fourth episode of Taming the Dragon webinar series. Again, so just a short introduction. My name is Carlos Guimarães, Senior Technologist at ZettaScale, and currently the lead developer of Zenoh Pico, which in very short words, and as Daniela said, is the Zenoh implementation for microcontrollers. So in today's episode, you'll learn a bit more about Zenoh and how it copes with microcontrollers and low-powered networks. Just as a reminder, here is the episode list of this webinar series. So if you missed the previous episodes, recordings are available. And besides this one, we still have two more to go, one on December 20, next week, and the last one on January 6. But first, let's do a bit of recap on the Zenoh concepts, especially for those that missed the previous episodes and still don't know what Zenoh is. So Zenoh is a technology that unifies data in motion, data at rest, and computations, really from embedded microcontrollers up to data centers. And it does that by providing a location-transparent API that is able to provide high-performance publish-subscribe, as well as distributed queries across heterogeneous systems. And it's also because of this location-transparent API that it facilitates the instantiation of geo-distributed storages and integration with third-party technologies in a very plug-and-play fashion way. So Zenoh is capable of running everywhere. So it's really a technology that can unify this heterogeneous ecosystem that we have today, from the embedded and constrained devices up to the data, the servers in the cloud. And it can run on top of different layers of the networking stack, as shown here in this figure. So it can run on top of the IP stack, for example, currently supporting TCP, UDP, TLS, QUIC, and others. But it can also run on top of non-IP protocols, so directly over the data link layer. And currently, we have some support for example, Serial, Bluetooth, and LoRa. Then we also have native libraries and APIs for many programming languages, but I will talk about it a bit later. So then Zenoh can also form a system with different kinds of topologies according to your needs and according to your system. So with Zenoh, you can have peer-to-peer topologies like a QUIC or a mesh, where nodes can directly exchange information with one another. But you can also have a more brokered mode where a node is acting as an intermediary in the communication between parties. But at the same time, you can also have more complex topologies where you have routers in the middle that are able to forward data to and from other peers and clients. For example, if we take this kind of topology that we have here in this slide, we can consider that the peers are robots that are part of a fleet, so they are doing robot-to-robot communication to coordinate their movements. And at the same time, they can use these routers to forward or to communicate in a more inter-fleet way. And then at the same time, in the bottom, we can have these clients that can be workers or people that are trying to access the robots to see what they are doing or to send any specific command. So as you can see, Zenoh does not really impose an architectural choice on how you deploy things, but it really gives you the freedom on the kind of topology you might want to build. And then regarding the code and the APIs, so regarding how developers implement your applications using Zenoh, we have available different APIs for different programming languages. So you can do things natively with the REST API, or use any of the other bindings in C and Python that are already available, but coming soon we will also have C++ and Java. But no matter what is the programming language that you choose, we always try to expose the same concept and the same set of APIs across the different programming languages, so you have the same feeling when using Zenoh. So for a more detailed getting started on how to use Zenoh and the different bindings, you can check the previous episode, in particular episode 2, where Luca Cominardi already did a very detailed explanation on the API usages. Still, I would like to highlight that Zenoh is natively written in REST because so not only to leverage its power for high performance networking, but also because it provides high level abstractions and guarantees memory safety. So we have our software Zenoh router that is also implemented in REST to leverage on the same advantages. So this was a very quick and brief introduction to Zenoh concepts, but I would really like to suggest you to watch our previous episodes to have a more detailed view on Zenoh. But now I would like to jump into this journey that has been supporting Zenoh on microcontrollers and low-powered networks, and highlight some of the challenges that we have been facing and how we end up overcoming them. Sorry. So the first challenge is the scale of systems. So where depending on the target device and the specific task that it will be performed, different MCUs with different CPU architectures and therefore different instruction sets might be selected, which in turn might also have different word sizes from 8 bits to 64 bits, for example. And if we take into consideration, for example, the word size, although it might be possible to represent integers higher than the word size, doing it will impact the performance. So with Zenoh, we wanted to accommodate these different systems and different bit configurations. So to do so, Zenoh is able to negotiate several parameters during the session establishment, allowing two Zenoh entities to adapt their operations based on this agreed set of features. And note that this negotiation affects only this pair of nodes or this pair of Zenoh entities and not the entire system, which can still operate under a different set of features. Then on top of this, a developer might still needs to define the target platform. So we can go on bare metal or rely on any kind of operating system, both general purpose or real-time operating systems that in turn can be open source or proprietary. And we didn't want to restrict Zenoh to a given platform. So we made our set of implementations platform agnostic, and at the same time that could be easily extended with minimal code extensions. So by doing it, so Zenoh can be integrated with whatever choice you do in terms of the target platform, but you might also, it also offers a smooth migration if you already have Zenoh integrated in your system and you decide to change your target platform. Another challenge is time, which is not guaranteed on microcontrollers, either because they don't comprise a real-time clock or simply because clock synchronization is not possible. In addition to this, usually they have broader time granularities, and many platforms still represent time as a 32 sign-bit integer, which will roll over in year 2038. So with Zenoh, we want to mitigate this issue. So we made timestamping opt-in, meaning that if your microcontroller is not synchronized in time with the rest of your system, Zenoh infrastructure will do it for you and provide the timestamps on the first infrastructure up. Still, if your microcontroller has the time synchronized, it can still timestamp the data. So another well-known challenge is regarding the available memory and space, which tends to be very scarce. So there are several reasons for this, like decreasing the costs of each one of these individual devices, the available area for memory, and also because of power consumption reasons. And because there are scarce resources, the tasks usually deployed in microcontrollers are also very specific and limited. So Zenoh and the set of implementations of Zenoh are also aware of this. So we, in such a way that we make sure that you have the most available space or the most available resources for your application itself. So Zenoh allows you to enable or disable features that your specific application might need or not. And by doing so, Zenoh footprint can be reduced, while sometimes even improving its performance by removing some unnecessary checks. And remember, as I said before, features are negotiated upon session establishment. Then energy efficiency, which is one of the key challenges. So we are talking about devices that target very low power consumptions and with limited energy. For example, sometimes a single device might be expected to run for years with its provided battery. And this is achieved by enforcing different sleep pattern modes or by adopting power-friendly programming patterns. So Zenoh is also aware of this and tries to help on this energy efficient challenge. And for that, it adopts not only power-friendly programming patterns in their implementations, but it also provides a set of features that make it energy efficient and allows it to cope with different sleeping mode patterns. Just to give you some examples, so Zenoh, as of today, is able to provide low wire overhead for data transmissions, so between 4 to 6 bytes, to support connectionless protocols and non-IP protocols, and even to support publish-subscribe with pool capabilities that can keep up with the different sleeping modes or other duty cycles. And then we also have networks that are low-powered as a way also to save energy and increase the lifespan of the devices. So these networks usually have very small MTU sizes, they have low data rates, and they rely mostly on gateway or mesh-oriented communications. And many times they don't even rely on IP-based technologies. So Zenoh, of course, is also designed to support such networks. So on top of, I just mentioned in the previous slide regarding Zenoh providing low wire overhead for data transmissions, the support for connection protocols, the support for non-IP protocols, Zenoh can also operate in different deployment models, like client to broker, client to router, and peer-to-peer. And on top of this, can also work over unicast and multicast transports. So in the end, applications running in this ecosystem must have a continuous balance between performance, functionality, footprint, and energy consumption. And depending on your application requirements, you might want to expose or consume data in different ways, and therefore you might want to optimize on specific aspects. And I think it is already clear with the previous challenges and some of the Zenoh features that were just mentioned, that Zenoh is flexible to accommodate your needs in any of these aspects. So here is just a summary of the Zenoh features that I have just mentioned and how they are mapped to each challenge that were also mentioned before. And note that this is not an exhaustive feature list. So you'll find out more in the previews and on the next webinars. So at this point, you might be wondering how you can actually use Zenoh in your microcontrollers. And this is where now we are going to introduce Zenoh Pico, our smaller dragon, let's call it like that. And in a few words, it's just a lightweight implementation of Zenoh for microcontrollers. But why did we decide to implement Zenoh Pico? So embedded systems and microcontrollers are still key in many application domains like robotics, automotives, and Internet of Things, etc. And many times they make use of constrained and low power networks. So WOPAN, LoRa, Bluetooth, serial, etc. So REST, which is the programming language for our main implementation, is still growing in the number of initiatives and adoptions into the embedded world, but we still think that it still needs to mature a bit more. So we had the need to natively address this family of devices, and that's why we developed Zenoh Pico as a small footprint implementation that is tailored and optimized to run on microcontrollers. So Zenoh Pico is fully implemented in C, both its Zenoh stack and the set of APIs. And since so we decided to go for C because because the embedded panorama still uses C as the programming languages, so around 80% of the entire embedded development. And Zenoh Pico was also implemented in such a way that it can be easily ported to many platforms, frameworks, and communication stacks. So just to give you some examples of what is supported today. So in terms of platforms, we have successfully tested Zenoh Pico on NXP, ESP, STM32 or Nordic Semiconductors boards, and integrated with many other frameworks, such as Zephyr, Arduino, EmbedOS, Expressive, and NetX, and also on Unix systems. And then in terms of communication stacks, besides the TCP/IP stack, Zenoh can also run today on other non-IP transports such as Bluetooth, LoRa, serial, and ESP now. And finally, Zenoh Pico implementation also adopts MISRA C guidelines to make it compatible with many industrial standards. And just for you to have an idea, so these are the types of devices that Zenoh Pico is targeting. And note that here we have a set of developer boards that are a bit more bulky than what goes in production. But we are talking about very small devices with constrained capabilities. And then from the perspective of the developer, it follows, so Zenoh Pico, it follows exactly the same set of APIs as the main Zenoh implementation, and in particular, the Zenoh C bindings. However, it has been tailored in some aspects to adopt a more idiomatic pattern to embed it, and this is mostly related to the Zenoh configurations, task management, or the key expression to string helpers. So now we are going to start a bit more this hands-on part, so I will be switching between slides and code. But first, let me just introduce the ownership model that we decided to have in Zenoh Pico and also in Zenoh C. And the idea was to replicate the same ownership model that we have in REST, so to make it more explicit to the user. And we wanted to do it because it can target a better memory management, where memory leaks can be easily identified and double free can be also avoided. So by doing this, the user will have a clear idea and understanding on what is owned by his side of the code and what has been loaned or moved to the API. So we have, as you can see here in the code, but I'm going to change to Visual Studio, we have this set of owned types, and then we have a set of helpers, which is move, on, check, and drop, which we use to handle these types. So if I move now here to Visual Studio Code, yep. So here I have a simple example that I just created with a config. So you can see here that when we create our default config, we have a own type. Okay, then I'm inserting some parameters in our configuration, and for that I'm loaning it to the API every time I need to insert. So the API will make sure that it changes my config and returns it back to me. So if I check what is the validity of my config after the insert, I should have it as valid because it has been created and it's on my side. So my config is valid here. So then we can do two other options. We can either move it to the API, and then it is no longer our responsibility to release it because the API will do it for us, or we might decide to drop it, which would be the equivalent to doing it free. So if I pass it to the API by using it to open a session, I'm moving it to our API, and when I run it again, so before calling the open, my config is valid. After it, my config is no longer valid because it has been already released by the API. In case I end up not moving my own types to the API, I can simply do a drop and the same will happen. So my config is valid, and then my config is not valid because it has been released. Okay. So going back to the presentation. Okay. Yeah, so this is it. Then regarding Zenoh related configurations. So while in more traditional systems, we handle configurations usually by file. In Zenoh Pico, we want to use configurations in a more idiomatic way for embedded. So in Zenoh Pico, we have two types of configurations, basically compile time configurations, which allow you to enable or disable features, and runtime configurations, which are kind of the same as in Zenoh C. And here on the right, we have an example on how Zenoh Pico handles the runtime configurations, which is basically as a key value pair, while in Zenoh C, it uses JSON5 file. Then regarding task management, we wanted Zenoh Pico to support both multi-thread and single-thread modes. So to do that, the user has explicit control over the read and delete tasks. For example, for the multi-thread, the user must spawn or destroy both tasks manually by including the following lines here on the right after the session establishment. And in case of the single thread behavior is intended, the user does not spawn any of these tasks, but instead it triggers the single execution of the read and delete task at its own pace. And then the conversion of a key expression to string format. So Zenoh Pico might not store the full string representation of a key expression in a given point in time in order to save memory. And for those that don't remember or didn't watch the previous sessions, so Zenoh allows you to do key expressions declarations, which will transform your key expression into a single integer. And this allowed us to really decrease the wire overhead. So because of this, you might not have the full representation of the string, of your key expression as a string. So in Zenoh Pico, besides doing key expression to string, you also have the option to resolve the string to which you must associate the session where it was declared. So we'll have a bit more time to look at the API during the hands-on part of this episode. But before that, let's just have a quick look on Zenoh Pico performance and how it compares with other solutions that are also targeting embedded and microcontrollers. So here we have some perfs that we did. So all code is on this of these perfs is open source in case you want to test it on your side as well. And in terms of throughput, we can see here that Zenoh Pico is over in several orders of magnitude when compared to DDS, XRCE, MQTT, or OPCUA. And for smaller messages of 8 bytes payload, Zenoh Pico can exchange over 3 million messages per second. And even for payloads of 8 kilobits, Zenoh Pico is able to send more messages than any of the other solutions for any kind of payloads. And here, note also that some of these alternative solutions were not able to send messages after a given payload size, as it's the case of DDS, XRCE, and OPCUA. Then, in terms of latency, Zenoh Pico in brokered mode has a performance very similar with the remaining solution. But when it goes peer-to-peer, it can reduce the value by almost 3 times, down to a minimum of 12 microseconds. Then in terms of wire overhead, and if we take the data as the periodic message that is recurrently used over time, Zenoh Pico reduces by half the overhead in comparison, for example, with MQTT. As for the remaining stages, that usually happens only a single time on the entire execution. And even though there are several negotiations going on Zenoh during the opening of a session, its overhead is the lowest or the second lowest of all these solutions. Still, I want to highlight that the critical stage here is the data, and for that, we are the lowest overhead in all these solutions. And then finally, here is the footprint of Zenoh Pico for different frameworks and for different network configurations. In summary, the Zenoh Pico core with all its features enables take around 40 kilobytes. However, if you disable most of its features by configuration, it's easy to get this value down to just 15 kilobytes. And in extreme cases, it can be even lower if we consider just the minimal functionality and that some manually tailoring of the Zenoh capabilities is performed. So after all this, can we say that Zenoh and Zenoh Pico are the same? And the answer is yes. So Zenoh Pico is just an alternative implementation of Zenoh in C, and it provides API portability with minimum tweaks. It is the exactly same wire protocol, meaning that it can interoperate with Zenoh, and it provides the same set of functionalities, but in a more lightweight fashion way. And it is C99 and MIRSA compliant. But let's move now to the more hands-on oriented part of this webinar, where we are going to do some live coding to show you a couple of demos. So in this first one, we will extend the demo of the previous webinar. So if you remember, Julian Enoch was showing a demo with the TurtleBot tree and in interaction with the Zenoh DDS bridge. So here we are going to extend it to allow a more immersive control of the TurtleBot by using a microcontroller, which is the one that you can see here in this picture, that whenever we tilt it, the robot will move. So for this, we have the ESP32 here that is connected to this MPU 6050, which basically contains an accelerometer and gyroscope sensors. And ESP is running the Arduino framework, and it is integrated with Zenoh Pico. Then we have a router at the cloud where the video stream, LiDAR, and other sensing information from the robot is being published and displayed. And on the robot, we are also running our Zenoh DDS bridge, which was explained in the previous episode. So more details, I will just refer to the recording. So now let's move again to the Visual Studio Code. Here, moving here. Okay, so to keep it easy, today we are going to use Platform.io, which is basically a tool that eases the project setup, that fetches all the dependencies that you might need, the build, and flashing it to the board. So we are going to use it for both hands-on and demos. So it's very easy to install. You just need to do pip3 install Platform.io. So here I already installed. So to create our project, so first you create the folder. I have already done it. And then you need first to identify what is the board where you are going to flash or that you are going to use. And for that, you can do PIO or Platform.io is the same. So typo here. So Platform.io boards, and it will give you the list of all these boards which are currently supported. So we will just grab for our, so we have its ID. And as you can see, they have just a couple of megabytes of storage or flash. So then whenever we have our ID, we can initialize our project. So P we need -B and our board identifier, and it will fetch dependencies and set up your project. So in this case, I have already done it before, so compile times are smaller, and it will create this structure in your folder. And in platform.ini file, you have some meta information on your project. So here we can see that they already included Zenoh Pico dependency, also the dependency for reading the values from the sensor. And then I had additional build flags. So in this case, I'm reducing the buffers, the transmission buffers to just 1,500 bytes, because I know that we'll not send messages higher than that. So I can simply decrease the buffer. So very easy to run. So to compile is just pure run, but before, let's see what I already have here in the template, although on the right. So this is the code that is basically connecting to the Wi-Fi, calibrating the sensor, and reading the values. Okay, then it creates a twist message and it just prints. So let's start by flashing this to the board. So first I'm going to connect it. So we can compile with PyRun. And then to flash, we can just do PyRun -t upload. So if everything goes right, the board should start, it will start be flashing. Yep. And then we will just see what is happening. Okay, so here we are also initializing the serial for monitoring. So we can just do PO device monitor -B, and we pass the baud rate that we configured, and that's it. So this board specifically, when we open the the monitor, it will reset. So it's doing everything again, connecting to Wi-Fi, calibrating, and then it's printing the message every 100 milliseconds. So I'm going to try to show, if I tilt the board, it will update the values either on the X and the Y values. So these are the values that now we are going to use Zenoh to send it to the robot. So before that, the robot is already here. So if you go to demo.zenoh.io, you can see. So you can see that someone now is on the corridor. It also has wider information, so it's very close to the right wall and have more space on the left one. And it also provides other sensing information like the battery and some other information on the accelerometers and the odometry that the robot is exposing. Okay, so now what we are going to do is to start integrating Zenoh. So I go back here. So first thing is to include our library. Okay, very easy, include zenohpico.h. Then what we will need is we'll need to create our session, and then we are going to publish the information by using a publisher. Okay, so here I'm going to assume that we are already aware of some of the concepts that were presented by Luca. So the publisher we are going to use to do recursive publish on the same key expression. Otherwise, we could go and do a put directly with the session, with our Zenoh session. Okay, so sorry. So we already defined our session and publisher as global variables, and now we will open the session after the sensor is calibrated. Okay, so we just have our default config. Here I'm already identifying the peer to where it is going to connect. Although if you skip this line, it will simply run our scouting mechanism. So we will discover whatever entities are on the network and connecting to one of those entities. Here we want explicitly to connect to the robot, and then we are using this config file to open, and then we are checking if the session, if opening the session was successfully or not. Okay. After opening the session, we will start our read and with tasks. Okay. This is mandatory unless you go in single thread, and in that case, you still need to run them explicitly. So in the second end zone, we are going to use the single thread. So I will explain a bit more on the second one. And then we define our publisher, or we declare our publisher. So we are going to do it with the default options. And we declared it, we own our session, we define what is the key expression where we want to publish, and then we check if it was successfully declared or not. Just one note here. So because Arduino doesn't support the generic macros, we need to be a bit more verbose here. Okay, so if you remember, well, I still have it here. In this previous example, we were just doing zloan, zcheck, and zdrop because it had the support for generics. But in this case, we need to go a bit more verbose. So we need to always to identify what we are loaning it. So the same for the config, zconfig move, zsession mode. Okay. So we have our publisher now, and then we want to use it to send the data. So for that, it's as simple as serializing the message, that we already have some helpers here that I already provided before. And then we just need to do the publisher put, to loan it the publisher that we just created, and to pass the buffer and its size. Okay, so if everything goes good, we might be able to control the robot. But first, let's flash it again. And when it starts, okay. So now I'm going to move here to our web interface. So whenever I'm going to tilt the microcontroller, we will see the robot here moving. So at this point, the sensor might be calibrating. And it's already connecting and sending information. So if I'm tilting it, as you can see, it's also moving. Okay. So going back here, so as you see, it was as simple as opening the session with a default config, declaring our publisher on the key expression that we wanted, and to actually publish the data. Okay, a couple of lines. It was more than enough to have this demo working. So going back here to the presentation. Yeah. So basically here is just for you to have a better understanding on the kind of flows that were happening in this demo. So basically we had the camera and the sensors sending the data to our Zenoh router in the cloud that was then displaying the data in this web server. But then the comments from the microcontroller were not going to the Zenoh router in the cloud, but instead they were going directly to the robot. So as you can see, we don't need to have a broker or a central point of connection. So we can really go decentralized on our communications here. So it is natural to me to say that Zenoh Pico provides a better solution for microcontrollers in order to interact with the rest of our ROS2 system. But here are some of the reasons why I believe that. So Zenoh Pico allows different communication models like peer-to-peer, client-to-broker, and client-to-router, while micro ROS2 only supports client-to-broker. Then in terms of transport, Zenoh Pico can be integrated with practically any transport available. Micro ROS2 is limited to IP networks because of TDS XRC. In terms of user API, Zenoh Pico, as you saw, is extremely simple API that tries to avoid error-prone behaviors. While on the micro ROS2 side, it's a bit more complex, and it will likely lead to unintended error behaviors. So Zenoh Pico is quite lightweight. You can configure the set of functionalities that you want or features that you want to enable. Micro ROS2 is more heavyweight. And then in terms of ROS2 interoperability, of course, both of them are able to do. In fact, you just saw it for Zenoh Pico. And then while developing this demo, we also end up porting the Turtlebot tree to run entirely on Zenoh and only using the ROS2 messages for an easy migration. And just to show you very quickly here a video. So first in this picture, you can see the Turtlebot tree burger that we stripped out the Raspberry Pi because we didn't need it anymore. We just had to plug our Wi-Fi interface to the OpenCR board. And then it was running Zenoh Pico on OpenCR board. And we had the same controller as I just show you now. And then we have a Zenoh router at the edge that is connecting both of these entities for their communication. And here is a short video of it. So as you can see, whenever you tilt the microcontroller, the robot is moving. And well, it was quite fun. It was very responsible. And we have a whole blog showing how you can also do it yourself. So now moving to the second hands-on, and here we are going to expose data. So basically here we want to showcase that you can bridge different communication technologies with Zenoh. Okay, so in this case, we are going to have a serial-only device that is exposing information to the IP world. So we have here this STM32 that is going to be running Embed OS, and it is equipped with DHT22, which is basically a humidity and temperature sensor. So the device is going to publish the sensed information to a local Zenoh router, which is running on my laptop via serial. And in turn, it is being, sorry, I'm trying to connect. It is going to send this information to this Zenoh router that is running, that is integrated with InfluxDB. And then we are going to monitoring the values with Grafana. So just waiting things. Okay. So we go back here to our Visual Studio Code. Yep. So I already have it open here. So this is just, again, a template on that we are going to flash to begin with. So we are just reading the values from the DHT sensor and to print them. Okay. So if we go now here, I can do the same. I could already, so here I already did the PIO run init, etc., etc. So let's go directly with flashing the board. So it's compiling. So most of the time, or sometimes it happens that it cannot flash, you cannot reset the target. So it might be that you need to reset it again and trigger the upload again. So now it went successfully. So now if we do IO device monitor, okay, so I have the wrong. Yep. Okay, so here I need to pass, let me see which one is my interface. TY. Okay, 2403. Okay, so I had this reconfigured, but it seems that he changed his name. So USB modem. Okay, here it is. And we can see that we are reading 2521 on as values. So now, and as before, let's integrate Zenoh Pico and expose these values. So first of all, and again, we need to import our libraries. Then we create our session, and again, our publishers. We are going to have a publisher for the temperature and a publisher for the humidity. And then we open our session. Same way as before, exactly the same code. And then our two publishers. So we declare one publisher for the temperature, another publisher for the humidity. So here is just a naming scheme that we have in our office. So we are already exposing some sensing information via Zenoh. Then I said that we are going to go single thread here. So on my loop, I will need to spin. So now to spin, we just need to call the read and the keep alive, so that if there is any message in the buffer to read, it will consume it, and the send and the keep alive, if there is something to send, because the lease is expiring, it will just send it. Okay, and then as before, we just need to serialize our values. In this case, we are just sending them as a string, and we just do publisher put. We want the corresponding publisher, and we pass the buffer. So let's compile it again and upload it. And in the meantime, I'm also running here the Zenoh router in my computer. Okay. So the Zenoh router is going to, so we already received the declarations here for both temperature and humidity. And if we go now to Grafana to see what is happening, we can see, so let me refresh. So you can see here that 1050 was the last value received. So he's sending one value every second and refreshing every 5 seconds, but I can force the humidity to go high. So, and we might see here that is going to update on the left side. Yeah, so we can see I just, I just breathed to the sensor and we have a spike here. Okay, so I have the sensor running for some time, and you can see here when someone arrived to the office and turned on the AC, the values increased because it was hitting the room. So yep. So as you can see, let me start presentation again. So as you can see, Zenoh can really expose values or data that is even from non-IP technologies and expose them to the IP world. And just a quick also demo here on where we are using Bluetooth. So on the left, so these two devices are connected via Bluetooth, and they are using Zenoh to send comments. So on the left side, we have these microcontrollers sending on and off comments, and basically on the right, now we are running it. It will receive the commands and turn on and off the light. So now you received off is off, and you will receive on, and it's going to turn on. So we have a similar demo using LoRa, but we didn't have the recording, so we will try to make a blog post on it later on. So yeah, so we are getting to the end of this presentation, so time to wrap up things. So we have a couple of minutes for questions. So in summary, Zenoh Pico is a lightweight implementation of Zenoh for embedded systems, microcontrollers, and constrained networks. It is able to achieve high throughput, low latency. It has a very small footprint and minimal wire overhead. And again, it adopts MIS-RESI guidelines to make it compliant with many industry standards. So don't forget to visit our Zenoh website, to check our GitHub pages, and to start it if you want. And you can also join our Discord server where the entire team will be there to provide support and to clarify some doubts that you might have. So thank you very much. And well, if you have some questions, now is the time. So now let me stop here. So now I believe that I can see some questions here. I think I need to press here. Okay, so they are not being marked as questions, so give me just 1 second. So I think they are in the chat. So question from class, Jan. The Crazyfly micro UAV as an STM F405 microcontroller, which is a Cortex M4 with some other specs, and communicates with Bluetooth low energy. Would it be possible to run Zenoh Pico on this drone? So on this board, we know that you can run Zenoh Pico. So the current code that is on the master and the release 060. Regarding communication with Bluetooth, so as up to now, we have only support for Bluetooth Classic and with the serial profile. But the experience that we have been doing with many other low-powered protocols is that it can run there as well. It's just a matter of providing the support and the implementation to Bluetooth low energy. It would also be interesting to know which framework are you using, because we might need to implement it for all the platforms. So if you have one in specific that you want to target, we can try to prioritize things on our site. So slides. Okay, regarding. Okay. So can I use Zenoh Pico today to interoperate with ROS2? So yes, as with any Zenoh application, and as we demonstrated in the last webinar, you just need to deploy a ROS2 Zenoh plugin bridge. So how would tasks work if you have a bare metal system and no threads, something like timer trigger interrupt service routine? So currently we don't support these interrupt service routines. It would be interesting to have indeed. So as of today in your loop, you need to run a spin. I think many other libraries are also following this approach. So you run the spin and basically it will read any message in the buffer, otherwise it will return. And when you call the keep alive task, or when you trigger your single execution of your keep alive, if there is something to send, it will send. Otherwise, it will just skip until the next time you call it. And this question was from Michael Pon. Sorry for mispronouncing it. Then, okay, another one here. Are there any users using Zenoh Pico in place of MicroROS2? If so, why? So there are more and more users starting to choose Zenoh Pico over MicroROS2, and the main reasons are the facility of using it, the performance footprint, and the set of transports or connectivities that Zenoh Pico offers in addition to MicroROS2. So another question here, can I find the source code of today's demo? Yes, we already have in ZettaScale Labs, we can share the links afterwards, but we already have a whole repo with several demos that you can clone and run them on your side as well. Then two last questions, and as I see here, so does Zenoh Pico support peer-to-peer? So yes, it currently does when leveraging, for example, on UDP-IP multicast. And what is required to be able to port Zenoh Pico to an embedded target, and how are these? So as of today, we have the core of Zenoh Pico separated from everything that is system specific. So if you have a new embedded target or even a new communication stack that you might want to integrate, there are just a subset of files that you need to extend to support this new platform that is basically going to interact with the system. Everything else on the code that is core to Zenoh Pico, it remains untouched, and we have this very specified interface between the system and the core of Zenoh Pico. And I think I don't see any more questions. And just in time because it's 1 hour sharp. So yeah, thank you very much for attending the webinar. If you have questions, you can go on Discord and make them there. We have me and the entire team that will be able to reply. And in any case, we are going to repeat this webinar at 6 p.m. So feel free to join again. Thank you very much and bye.